my name is Atkunda Patience Jafu. I am going to teach you about the SIR model. Now, many countries of the world have been faced with outbreaks, epidemics, and pandemics, and these have led to loss of lives, and it is very important that when such situations happen, we study the dynamics of the disease to be able to know how best to come up with targeted interventions that can save lives and contain the outbreak. One of the ways to do this is to use the SIR model. The SIR model is a compartmental model that divides the population into 3 compartments. One compartment is the susceptible, now, the susceptible are people who are not yet infected but are likely to suffer from the disease. And then it also has the infected, the infectious, and these are people who already have the disease and then they recovered. And these are people who have recovered. So the SIR model divides the population into 3 compartments. These are the susceptibles, the infectious, and then those that have recovered from the disease. It has 4 assumptions. One is that there will be an interaction between the susceptible and the infectious for the disease to progress. And then that once someone has recovered from the disease, they will gain immunity over this disease and they will not suffer from it again. It also assumes that this population is closed, therefore there are no births coming in and there are no deaths. It also assumes that the rate of infection that leads the susceptible to become infectious is constant, and therefore, and then the rate of recovery is also constant. Those are the 4 assumptions of the SIR model. So it also, in the SIR model, the susceptibles will move, will always have a way they will move from their compartment to the infectious compartment because of the interaction between those that are susceptible and those that are infectious. And again, the infectious will always move from their compartment to the recovered compartment after an intervention. Now, there are 2 very important variables in the SIR model. One is beta, which is the rate of infection, which we also call the transmission rate. The transmission rate. And then gamma, which is the recovery rate. So the transmission rate is the one that is responsible for someone moving from the susceptible compartment to the infectious compartment, and the recovery rate is responsible for someone who is infectious to move to the compartment of the recovered. Now, at any one point in time, this population, because we said it is closed, the susceptibles at any one point in time plus the infected at a particular point in time plus the recovered total up to the total population, which is N. And remember, we said N is constant. So Next is that when this happens, for someone to move from one compartment to the other, for example, the susceptible moving from their compartment to the infectious compartment, there will be that one infected person that will infect the susceptible out of the total population. So remember we said the total population is constant in the assumptions we already stated. So for one to move from one compartment to another, there is going to be an interaction, for example, from the susceptible compartment to the infectious compartment. An infected person will need to interact with the susceptible person. The individual member of the susceptible compartment moving to the infectious compartment will have an infected person interacting with the susceptible person. So that's one infected person out of the total population interacting with one susceptible person. So that's one times the rate of transmission, or we also call it the rate of infection. The rate of infection. So that will give us B out of N times I. This is for an individual member of the susceptible compartment. But then we need to scale this up to the total population of the susceptibles, and this means we are going to multiply by S, which is the population of the susceptibles. So that gives us beta out of N times SI. So then we go to the, so here we are having beta out of N SI. Then we move to the infectious compartment. So for an individual member of the infectious compartment to move to the recovered compartment, we will have the recovery rate times the one individual, which is 1. So because this is an individual, we are considering the population of the infected, then we are going to multiply by I, which is for the infected compartment. So this gives us gamma I. So this moves the people who are susceptible from their compartment to the infectious compartment, and then this moves the infectious people to the recovered compartment. And this is for a discrete unit in time, for example, weekly or daily. You remember during the COVID-19 when we were always updated with the daily cases, the weekly cases. So that's, we can relate that to this. But then we know that the reality during an outbreak is that this is continuous. So we need to be able to calculate the overall dynamics of this outbreak by considering how people come into any compartment and how they get out of the compartment to another compartment.